Okay, we're going to continue on. We got into chapter 2, I think, and so we'll continue on there. So really, we got into chapter 2, and we were talking about and sort of finished up last time about measurements and how to, again, properly take a measurement. Remember that when you do take any type of measurement, there's some degree of uncertainty. There's some degree of estimation that occurs when you take a measurement. It is based on obviously the piece of equipment that you're using as to sort of where the estimation or sort of uncertainty lies. As we talked about, you always want to really look for sort of two markings on your scale. Again, we refer to those sort of as the large markings and the small markings. And as we talked about last time, I think we looked at a ruler, looks something like this. And again, a reminder that the large markings usually actually have numbers associated with them. So that's a 1 and a 2. So obviously the difference between that, as we talked about, is 1 centimeter. Then we want to really count up how many of the small markings there are between those large markings. And remember, it's important to count it sort of correctly. So again, you are going to start, as we talked about last time, past the last large marking, and you're going to continue to hit the next large marking. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 sort of small markings between them. Again, if you're not 100% sure what that would mean, you can just take the large markings and divide it by 10, and that will tell you that it is 0.1 centimeter. So when we do take a measurement, like we're measuring maybe arrows or something like that, there should always be certain numbers that really, no matter who looks at it, everybody should agree it is at least, whatever that is. And in the case of this, as we saw last time, 1.1 here, 1.2, 1.3, 1.4, and 1.5. So once again, everybody should agree my arrow is at least 1.4, and that is what we would want to definitely record. And again, sometimes these numbers are referred to as all the certain numbers. And again, those are sort of non-debatable numbers. Again, everybody should sort of really agree is at least that. Again, as we talked about last time, not exactly 1.4 here, not exactly 1.5. And really, this is where sort of our estimation or uncertainty comes into play. Again, in this case, I could kind of look between them and go, well, maybe I think it's just a little less than half. And maybe I'll record a 4 here. And this would be my first uncertain number. And obviously always the units there. And again, whenever we take a measurement, you should always record all of the certain numbers plus that first uncertain number when you're taking a proper measurement. And a reminder that that essentially means that that is really how many significant figures it has. And again, in this case, this would have 3 significant figures. The uncertain number is always the last significant figure. So in this case, it would be that last 4 would be where we're saying. So essentially what we're saying here is I think it's 1.44 centimeters, but maybe it's like 1.45, maybe it's 1.43, but the uncertainty is falling there in the second decimal place is where we're not 100% sure of, which is not terrible or bad on that sense. We could also, as we talked about last time, typically speaking, you could typically go to one more place to the right of the smallest sort of marking. So in this case, the smallest marking was 0.1, the first decimal place. We could actually take the reading one more place to the right of that. And in most cases, probably 9 times out of 10, you could do that just simply. You could take the reading to one more place to the right of the smallest marking. We also talked last time that if you are really confident about what the smallest markings represent, and you're not maybe 100% sure of how far you should take the reading to, all you simply have to do is just take the smallest marking and divide it by 2, and that'll get you something like 0.05 centimeters, basically. And really, you don't have to worry too much about this other than that takes you to 2 decimal places. And again, that is how far you should take the reading in this case. So if you're unsure but are sure of the smallest marking, just simply divide it by 2, and I'll tell you basically how far you should take it. If you divide it and you get a number that's like the first decimal place, that's how far you should take it. If you get one, like for example, we had the smallest markings being 2 milliliters, right? We divided by 2, it came to 1 milliliter, which is a whole number. And again, that in that case, that would be the best that you could do. Any questions on how to take measurements there? All right, so I don't think we did some of these. So let's go through a few of these. So here, why don't you take for a moment here and record what you think the proper measurement should be of this? Okay, so let's take a look at it. In this case, our large markings is basically 1 centimeter. Again, that's a 4 and a 5. When we look at the small markings in this particular case, there are none, right? So in this particular case, our large markings and our small markings are actually the same. So this also would be 1 centimeter, again, because there's no other markings between those guys. So that is basically going to be our large markings and our small markings in this case. That means it's at least 4. And again, at this point, this is where the estimate is not exactly 4. It's not exactly 5. Maybe it's halfway there. 0.5 centimeters, this being my certain number. This being my first uncertain number. And again, in this case, this would have 2 significant figures, with the 5 being the uncertain number. Again, if you were able to figure this out, if you divide that by 2, gets you 0.5, which is 1 decimal place. And again, that's how far you should take the reading too. Any questions on that? So this does sometimes happen. Sometimes there's just one set of markings, no other little dashes or anything like that. So it is possible, like we see in this example, that the large markings and the small markings basically represent the same amount in this case. And you basically approach it the same way as any other. Any questions on that one there? Yeah. And they agree with us, which is good. All right. Now, if we look at this one here we have our large markings, which again is going to be 1 centimeter. This time we do have small markings. And again, if we look, we have 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Bad shot on that 10 over there. So again, the small markings here are going to represent 0.1 centimeter, which again, you could get by taking 1 divided by 10. We'll tell you what each of those will be. Here, we're right around that 4.5 marking. This is 4.6 there, which looks like it's just past where that is. So that's basically 4.6. So it is for sure 4.5. Once again, in this case, this would be our certain numbers. And again, they estimate it's about halfway between the next dash. So they did put a 5 there for our first uncertain number. And again, this would have 3 significant figures. The last 5 there would be the estimated digit or uncertain digit in this particular case. Any questions on that? Again, you could do the same thing. 0.1 for the smallest divided by 2, 0.05, 2 decimal places should take the reading to 2 decimal places. So again, that's a way that you could kind of figure it out. We also talked about last time 2 other important things. You want to make sure that you do maintain the proper sort of reading based on the scale that you see there, which again, if you're exactly on a number like in this situation here, or if we were on using this ruler and we were exactly on a dash or something like that, you would need to insert a 0 to maintain the 2 decimal places. And again, you don't want to lose that sort of significant figures as we talked about last time. And also you shouldn't add extra zeros if you can't do that with the scale that you have as well. And again, that is no good as well. And that's what we see here. This one is dead on the 3. And again, this is the same ruler we looked at the first one here today. And again, the large markings and the small markings represent 1 centimeter. So we know because the large is 1 centimeter. The small is 1 centimeter. We could go one more place to the right of the smallest marking, which would be the first decimal place. And because of that, we would need to insert that 0. And that would give us the proper 2 significant figures here that this measurement should have, with the uncertain number here being the 0, as opposed to if you just wrote 3 centimeters, this now has 1 significant figure where the uncertain number would actually be the 3. And in that case, what you would be saying is, if you recorded just 3, as we talked about last time, you're saying, I think it's 3, but maybe it's 4, or maybe it's 2. And again, if you just look here, you just made a lot of error there, right? So you inserted a lot of error that you really shouldn't have based on this scale, because you do have the ability to go out to that first decimal place. And again, by losing that 0, you made your measurement worse than it should be based on the scale that's there. So again, by going 3.0, which is how you should record it, you're saying, I think it's 3.0, maybe it's 3.1, maybe it's 2.9. So you're saying my error based on this scale is in that ballpark, which obviously is a much better measurement than, I think it's somewhere like this, right? Somewhere in that sort of football field. Any questions on that there? Yeah. All right. So thank you very much. Why don't you give this one a go? What should be the proper measurement? I'll put the 9 should go here, the 8 should go there, and the 10 actually should go there. So we'll just do it that way. A little bit all over the place. So how long is the red line here? All right, so let's take a look here. Again, looking at our large markings between, say, 9 and 10. Our large marking is going to be 1 centimeter. Again, if we look at the little dots here, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So our small markings, again, dividing that by 10.1 centimeters. So it is at least 9.1, which would be there. 9.2 looks pretty darn close to it. So 9.2 is definitely our certain numbers. In this particular case, because we have the smallest markings as the first decimal place, we can typically go one more place to the right, which means we do need to insert that 0, and it should be 9.20 in this particular case, with this being our first uncertain number in this case. And again, it would have 3 significant figures. Any questions on that there? Go. All right, so now that we sort of talked about where significant figures come from, and obviously they come from, as we talked about, measurements. So measured values have a certain number of significant figure based on your equipment. There are, as we, I think, talked about before we got going here with this measurements last time, exact numbers. And again, exact numbers are different than measured numbers. Exact numbers are numbers that are either something that is counted or something that's considered like a definition, like 12 inches equals 1 foot, something of that nature. Something that's counted, again, if you had like apples on the table, you would just count how many you have. You're not going to do a science experiment or a big measurement to try to figure it out. So when we look at significant figures, there are certain rules that we want to follow when we're counting significant figures. And let's go over sort of those rules for significant figures. The first rule for counting significant figures is any non-zero is significant. So whenever you have a non-zero number, it is considered a significant figure. You got 4, 5, 2, 6, 8. By the way, when we start counting, for example, significant figures, we always count left to right, and we always start counting once we hit the very first non-zero. So if you're trying to figure out how many significant figures there are in a particular number, you should start left to right, and you shouldn't start counting until you hit that very first non-zero. So in this particular case, that definitely is a non-zero, which would make it significant. This guy is a non-zero, 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 and non-zero, which means every single one of these digits here are significant, and this number would have 5 significant figures in this particular case. Now, the thing that gives people really a hard time when they're doing significant figure are zeros. And there are a few different types of zeros that we actually come across. So we'll start with the first zero, which is sometimes referred to as a leading zero. And leading zeros are not significant. So leading zeros are not significant. You could have as many leading zeros as you want, and they're all going to be pretty much not important. Now, all the non-zeros that come before that first, all the zeros that come before the first non-zero are not going to be significant. So if we look at something like 0.000323, again, starting left to right here, these are all zeros. This is our first non-zero, and that is where we should start counting our significant figures. All these zeros that came before it are not going to be significant, kind of like placeholders to kind of keep the number where it should be. Then this would be significant, this would be significant as there are non-zeros. So this number would have 3 significant figures in this particular case. Any questions on that one there? The next type of zero is a trap zero, a captive zero, a trap zero. And those are going to be significant. So these are zeros that find themselves between 2 non-zero numbers, and they will be significant. So if you have something like 4004, once again, we would start counting here, and that would be significant. These 2 zeros are trapped between the non-zeros, which makes them significant as well. And lastly, the 4 at the end would be significant. So this guy here would have 4 significant figures in this particular case. Now, probably the zero that gives people the hardest time is what is sometimes referred to as the trailing zero. And those are the zeros that come basically at the end of a number. And trailing zeros, the reason why they give people a hard time is they can be significant or may not be significant. And really what determines whether or not a zero at the end is going to be significant is there a decimal point anywhere in the number? So if there's an actual decimal point written in the number, then the zeros at the end are going to be significant. So if there is a decimal point written in the number, the trailing zeros will be significant. Now, it actually does need to be written in the number. It is not one of those ones where you just kind of assume it's there. It actually has to be written in the number for it to count. So, for example, if I had a measurement like 600, this would have how many significant figures? It would actually only have 1 significant figure. It would be this guy here. These zeros at the end would not be significant because there is no decimal point written anywhere in the number, and this would actually have just 1 significant figure. Now, if you went 600 and you put a decimal point there, now how many does it have? It would have 3 because there's an actual decimal point written in the number. These guys are going to be significant, and this guy would have 3 significant figures. So really, what is the difference between these 2 numbers? The first number has 1 significant figure, which means the uncertain number, by the way, are the estimated number. And the first one here is which number is the estimated digit? It is the 6, because there's only 1 significant figure, right? So it's got to be that one, right? Now, what that is basically saying is, I think it's 600, right? but maybe it's 700, or maybe it's like 500, right? That's a pretty big room for error, right? Now, when we write it like this, the uncertain or estimated digit is which one? It's the very last zero. This is the estimated digit in this case because it has three significant figures. And basically, when you're doing that one, you're saying, I think it's 600, but maybe it's like 601, maybe it's 599 because the error lies all the way over there on the right. Which one's a much better measurement? It is this one, right? Because you're able to move the error way over to the right, right? So whenever you're able to kind of move the error or uncertainty to the right, it makes it a much better measurement than if the error or uncertainty is to the left. This also brings up a really good point that sometimes people always think that the uncertain or estimated digit is always the last number that's written, and it is not, as the case of the 600 there, the first one shows you. It should always, though, be the very last significant figure that is written. Yeah. And so sometimes, especially the lab likes to throw that one out there. They used to do 12,000 and go, which one's the estimated digit? 12,000 with no decimal. So they used to do like this number. I think they might have changed it over. She might have changed it over to yours, but 12,000, right? This would have how many significant figures written like this? It would have two. And in this case, the estimated digit would actually be it would be the 2, yeah, because those are the two significant figures, the 1 and the 2. Again, not the last number written. So again, sometimes people get in the habit that it's the estimated digit is always the last one written. And it is true in a lot of cases, it is a lot of times the last one written, but it may not always be the last one written. So the way you want to think about it is it should always be the last significant figure that is written in that number. And that's where the uncertainty or estimation sort of happens. Any questions on that there? We also talked about, for example, scientific notation, right? And remember that when we talked about scientific notation, kind of chapter 1 there, that is n times 10 to the n. Remember that when a number is written in scientific notation, any numbers that come before the times 10 part, these will always be significant figures. So if you have something written as 1.25 times 10 to the 3, all three of these guys are significant, and this number would have three significant figures. If you had 1.0 times 10 to the 4, again, this would actually have two significant figures. So if you have a number that is written in scientific notation, whatever the numbers are that comes before the times 10 part are always going to be significant. Also, a mistake, and a very common, again, mistake that people make is they'll have a number in scientific notation, and for some reason they'll turn it into like a decimal sort of number, and then not count the right number of significant figures. So if it is written in scientific notation, you should count the significant figures based on how it's written in scientific notation. By the way, when you go from scientific notation to decimal form or backwards decimal form to scientific notation, you really should try not to lose any significant figures along the way. You really shouldn't. You should have kind of the same number of significant figures as you go in either place. One of the benefits, as we also talked about in the last chapter, maybe it'll make a little bit more sense in this chapter, is again, because you could kind of control the number of significant figures when you write a number in scientific notation. Sometimes, again, the only way to give the answer to the proper number of scientific significant figures is to write it in scientific notation. So, for example, if we had that answer of 12,000, right, and we wanted three significant figures, right? There is no way to do that without doing scientific notation, because why can I not just do this? Is that three significant figures? The way I wrote it is actually three significant figures, 120. That number I just wrote is 120, right? The original number was 12,000. Is there a difference in the meaning of those numbers? There's a big difference in the meaning of those numbers, right? If I owed you $12,000 and gave you 120, said, here's three significant figures, you're not going to be super happy with me, I imagine, right? So, sometimes people do some weird rounding to try to get to the right sig figs, but you never ever want to change the meaning of the number. And clearly there is no other way to get the three significant figures. You put a decimal at the end, which keeps it at 12,000. But now how many significant figures do I have? I have 5. Again, not what we're looking for in terms of 3. So the only way you could do it is go 1, 2, 3, 4 and do a 1.20 times 10 to the 4. Now I have 3 significant figures, and by writing in scientific notation, it keeps the value of 12,000 basically. So sometimes that does happen. You're doing a calculation, you're like, oh shoot, I need like 3 significant figures, but there's really kind of no way to do it in decimal form. So again, that's really where you can kind of use scientific notation to help you, because you can control it. Again, if I needed, say, 4 significant figures, I could just add an extra 0 there and do 1.200 times 10 to the 4, and I would have 4 significant figures. So sometimes that does occur. Any questions on that there? So if I have this number here of 0.00043200400. We'll call it centimeters. I'm not sure. All right, how many do we think? 8, and what was their number? Okay, let's see. I don't know. I was just writing numbers. Let's see here. So we're gonna go left to right. So all of these, right, are not going to be significant because we do not start counting until we hit the very first non-zero. So sometimes people think, well, hey, don't these come after like the decimal point? So shouldn't they be significant? And they're not. Again, you don't start counting your significant figures until you hit the very first non-zero. So that would be significant. So with that, these are 2 zeros that are actually trapped between 2 non-zeros. So they would be significant. The 4 would be significant. That now leaves us 2 zeros at the end. Are they significant? That is yes and no. That is both answers. So the answer is yes, because way over here, there is a decimal point in the number. A reminder that the decimal point does not need to be holding the hands of the zeros at the end. They don't need to be near them. Just needs to be anywhere in that number for them to be significant. So both of these would be significant. I'm going to go with 8, which I think I heard earlier. So that's good, right? That's good. So 8 significant figures in this case. That has every zero I think you could have, maybe. Yeah. Any questions on that one there? Or significant figures there in general? All right, so let's take a look at some of these here. Again, we got 4.5, so those are all non-zeros. So if we kind of bring them up. So 2 significant figures. Again, starting here, those are all non-zeros, going to give us 5. Here we have 3. Again, that's a trap 0, which would make it significant. And here we have 4. Again, our trap 0 would be significant as well. Coming this way, we have 50 written like this. Once again, in the case of significant figures, we're not just going to assume there's a decimal point at the end. It needs to actually be written to be counted. And since there is not one written, the 5 here, right, would be the only significant figure. It would also be the estimated digit in this one as well. So this would be our estimated digit and the only significant figure. Here with the decimal point there, that's going to make these 2 zeros at the end significant. And obviously our original 2 numbers, which are non-zero, significant as well, which gets us to 4. Here we have scientific notation. So again, just going to take it right out of the scientific notation, not going to try to convert it into anything else. And there's only 2 numbers before the times 10 part. So 2 significant figures. Here there are 3 numbers, which would give you 3 significant figures in this case. Any questions on any of those there? We'll come this way. We got all these zeros are not going to be significant because, again, we don't start counting until we hit that 4, which is our very first non-zero going left to right. and that's the only number left. So that is 1. Same thing here. We're not going to start counting until the 7, and the 7 and the 5 are significant, which would give us 2 significant figures. Here, we would start counting at the 8. The 5 would be significant. Once again, we got a lot of zeros there, but there is no decimal point written, so none of them are significant. They're really just kind of holding the place to keep the value of the number what it needs to be, and it would be 2. Again, here in this case, the uncertain or estimated digit would be the 8, the 5, the 0. Which one? It would be the 5 in this case, right? The 8 and the 5 are the only 2 significant figures, the 5 being the last significant figure. So that is where the estimated digit would be. Here again, we run out of significant figures right about there, as the rest again are zeros with no decimal point anywhere in the number. And that is how we get to 3. Same thing here. Again, all these are non-zeros, so every single one of these digits and each of these measurements are going to be significant. So we got 4, 2, 3, and 5. Again, our zeros between going to be trapped and significant. So that's going to pretty much do all these guys as significant. The only zeros here really that are not significant are these zeros, which are leading zeros here and here as well. But all the other zeros should be significant as well. And again, no decimal versus decimal, going to make those zeros significant. All right. Any questions on how to count significant figures? So it is really important to try to give your answers to the proper number of significant figures. We're going to talk about when we do calculations, how we figure out sort of, where we should end up with in terms of answer. But it's also important to be able to do that is to be able to recognize how many significant figures there is as you kind of go through your calculation as well. Again, these are all going to be not significant, these zeros. They all come at the end, and there is no decimal point in any of those numbers. So none of them are significant. So just go left to right, and we got our 2 significant figures there, our 2 there, and our 3 there. And as we talked about in scientific notation, this would be 3 significant figures, 2 significant figures, and again, a bunch of them there, but we have 5 significant figures in this particular case. So as I mentioned before, if you have a number that's in scientific notation and you need to figure out significant figures, look at it written in scientific notation and figure it out based on that. Again, I've seen a lot of people just try to convert it out of scientific notation and then give the wrong number of significant figures when they do that. So it's actually a lot easier just to find the sig figs if it's written in scientific notation, because all you have to do is count all the numbers before the times 10 part. All right. All right, so why don't you take a few here? Why don't you identify significant and non-significant zeros in each of them and write the number in proper scientific notation. As I mentioned before, as you go from decimal to scientific notation, you should not lose significant figures. So figure out how many sig figs and write it in proper scientific notation, each of these answers. Okay, let's take a look. So we'll start with the first one. We might as well just figure out sig figs. So this first number has how many significant figures? It does have 4. Once again, we're not going to start counting till we hit the 2. That would be significant, significant, significant. The 0 here is going to be significant because there is a decimal point written in the number. So it would have 4 significant figures. Remember, proper scientific notation is a number between 1 and 10. It could be 1, but not 10. In this case, we would need to move the decimal to the right a few places. 1, 2, and 3, which would give us 2.650 times 10 to the minus 3 meters. Again, when we turn it into scientific notation, because it has 4 significant figures, I need to keep 4 significant figures here in my scientific notation. Again, we should not lose any along the way when we do that as well. Question on that one there? Okay, we look at the next one. Next one has how many significant figures? It does have 5. Everybody here is significant, including the 0, because it's a trap 0, so everybody's going to be significant. So it does have 5 significant figures. Here we would actually just need to go one place to the left there to get it to a number between 1 and 10. Because it has 5 significant figures, I do need to keep all of those numbers in my scientific notation. Again, I cannot lose any significant figures when I turn it into scientific notation. So you should always maintain the proper numbers, significant figures, as you go from sort of decimal form to scientific notation. Lastly, there, I don't see a decimal. I was wondering if there was one. How many significant figures does this one have? It is 4, and it actually would be just here, right? These, again, are going to be trailing zeros that are not going to count, as there's no decimal actually written in the number. So in this case, in terms of scientific notation, although there is not a decimal written, we do assume it's here, and we would move 1, 2, 3, 4, 5, and 6 places to the left. And that would get me 1.044 times 10 to the 6 liters. Again, keeping my 4 significant figures. In this case, I would want to actually drop the 3 zeros there at the end for my scientific notation. Otherwise, if I put it in my scientific notation, I would then have how many significant figures? I would have 7 significant figures, right? If I put those 3 zeros in, which again, all of a sudden I went from something that had only 4 significant figures to something when I put in scientific notation now has 7. So it got much better when I put in scientific notation, which should not happen. Yeah. Any questions on any of those there? All right. So we got that. Got that. Perfect. All right, so we talked a little about exact numbers, but once again, exact numbers are those obtained really one of two ways. As I mentioned, something that is counted, really no measurement taken. Again, as you can see, if you have cookies on the table or a couple of baseballs on the ground, you're just going to count them. Also, more commonly where we come across them is definitions, like 12 inches is equal to 1 foot. That's what's known as an equality. An equality is basically two things that are on different unit scales, but represent the same amount of something. So when we talk about sort of the length or the distance here, 1 foot is equivalent to 12 inches. They basically represent the same amount of distance. Same thing here, 1 kilogram is equal to 1,000 grams. So what is the deal with exact numbers? Exact numbers could pretty much have unlimited number of significant figures. So they could have as many significant figures as you would like. And really, the place where we kind of take exact numbers into account is when we do calculations. And the way we take it into account is we ignore them. And we ignore them in terms of their contribution to our answer, because I may say this number has 4, and you may say, hey, it has 3, because it could have as many as you like. So because of that, whenever you're doing a calculation that involves anything that's basically considered an exact number, we don't have to really consider its effect on the answer we're going to give in our calculation. The only thing that we do have to take into account in terms of our answer in our calculation is actually measured numbers that have a certain number of significant figures. So when we do calculations, we really just look at numbers that have significant figures to help us decide how far we should take our answer to. And we're going to talk about those rules shortly as well. But if you come across something that's an exact number, you don't really need to worry about it. And again, these are all exact numbers. We have some equalities. Now, there are 2 types of units, which I think we might have touched upon early on in this chapter. There are the English units or the US units, and there are the metric system. And if you are using some type of equality or definition that is a US to US definition, like 12 inches equals 1 foot, is considered an exact number. If you're using something that is considered a metric system to metric system conversion, like 1 liter is 1,000 milliliters, like we see here, 1 kilogram is 1,000 grams, those are also considered exact numbers. The only time you would have to take sort of a conversion factor into account, and it's not necessarily considered an exact number, is if you do a English to metric conversion, then you do have to kind of take it into account, like how many milliliters there are in a quart. So milliliters being metric, quart being more English type of unit, and you would have to kind of take that into account. It would not be considered an exact number. There is a metric to English conversion that is considered an exact number, and that is 1 inch is exactly 2.54 centimeters. So although that is a English to metric conversion, it is considered an exact number. But for the most part, if you kind of cross over, and we'll see a little bit later on in this chapter when we do some conversion problems, but if you cross over from sort of metric to English or English to metric sort of conversions, you usually do have to kind of take that into account. You're usually good to go if it's metric or US sort of conversion. You don't have to worry about it in terms of your calculations. So for each of these, right, we want to determine are the number of significant figures, if it is measured or if it's an exact number. 3 coins would be, it would be an exact, right? Again, that would be something that you would count. The diameter of a circle is 7.902 centimeters. That should be a measured value, right? And how many significant figures would it have? It would have 4, so that's an exact. That's a measured with 4 sig figs, as all those would count. And 1 hour is 60 minutes would be an exact, right? Again, that's going to be an equality, and that is just, metric to metric, time to time, basically, sort of conversion. All right, so for each of these, how many sig figs are we looking at on the first one? It does have 2. Again, we're going to start counting here. 0 is going to be significant because of the decimal point, so 2 sig figs. Next one would actually have 4. This would be significant. Trap 0 is significant. 5 is significant. Once again, the 0 at the end becomes significant because of the decimal point that's there, and that would be 4 significant figures. C has just 1. Again, all these are not significant. They're all still considered leading zeros because we have not hit our first non-zero. And again, that's where we would start counting. And this would be 1 significant figure. And lastly, D would have 3 significant figures. Once again, our 0 at the end is going to be significant because there is a decimal point written in the number. Any questions on any of those there? All right. So take a moment and watch you do these A, B, and C. Which one has 3 sig figs? Which one are all the zeros significant? And how many sig figs in the last one? So take a moment and pick out the right answer for each of those. All right, let's take a look, see how you're doing. We'll start the first one. We're looking for 3 significant figures. 1, 2, 3. Which one? Yeah, number 2 has 3 significant figures. Again, we would start counting here, significant. This guy would actually have 4 significant figures, as the 0 at the end is significant. And the guy over here would actually have 4 significant figures as well, as it's 4 numbers before the times 10 part. We're looking for which one has all the zeros that are significant. 1, 2, 3. What do we think? 2 and 3 is correct. Here, these guys are not significant, which eliminates obviously the first one. These guys would be significant because of the decimal. And this is in scientific notation, which means all those zeros are going to be significant as well. So it would be 2 and 3. Lastly, 5.8 times 10 to the 2 has 3 significant figures. So again, what will happen sometimes is, like I was saying before, somebody will have this number and they'll turn it into sort of decimal form and write it like that and go, it has only 2 significant figures, right? Because they didn't really do it correctly. So again, you don't want to do that. You want to look at it there when it's in scientific notation and count it. Any questions on that there? Is good. Yep. All right. All right, then let's get to what we should do when we're doing calculations. And just as important as identifying how many significant figures there are in a number, it's also really important whenever you do a calculation to really try to give your answer to the proper number of significant figures, whatever that may be. So there's kind of two types of math that we do typically speaking, or two kind of groups of math that we do typically speaking. So when we're doing scientific notation or significant figures in calculations, if we multiply or divide, so either one, either multiply or divide, the answer should have the same number of significant figures as the number with the least number of sig figs. So if you're multiplying or you're dividing, your answer you should end up with should be exactly the same number of significant figures as whichever number in your calculation had the least. So if I took 425 and I times it by 3.2, when I look at this, I am multiplying, which means this number has 3 significant figures. This number here has 2 significant figures. That means when I get my answer should have 2 significant figures. So again, it is always a number with the least. So if I pop that into my calculator correctly, maybe 4.2, 3.2. On my calculator, this is what it spits out at you. Like a 1, 3, looks like 6, 0. Reminder, your calculator does not give you the proper number of significant figures or put in scientific notation usually or anything like that. So I need 2 significant figures here, which means technically speaking, I should end up at 1400. Should I put a decimal point at the end? I should not, otherwise I now have 4 significant figures, right? I should not write just 14 because then it's not the same meaning, right? So again, we want to be careful not to do any extreme rounding to get the right number of significant figures. I could also do scientific notation if I wanted to, 1, 2, 3, and do a 1.4 times 10 to the 3. So if you multiply or if you divide, your answer should have the same number of significant figures as whichever number in that calculation, again, has the least number of significant figures. Any question on that there? Now, it works the same way, like I said before, if you divide or multiply. The other sort of common calculation that we do is add or subtract. So that's sort of the other thing that we do. And if you add or if you subtract, you are actually not looking at significant figures. You're actually looking at decimal places. So when you add or subtract, your answer should have the same number of decimal places as the number with the least number of decimal places. So we are looking at decimal places and adding and subtracting. So if I did 1.111 plus 2.3 plus 4.001, and I added all those together without the benefit of a calculator. We'll try that there. There, keep it all lined up there. We got like a 2, a 1, a 4, a 6, and a 7. So we end up with 7.412 when we add those together. At this point, what we are looking for, once again, is not significant figures in this case. and that is because we are adding or subtracting. We're looking at decimal places. So this first number has 3 decimal places. Second number has 1 decimal place. Last number actually has 3 decimal places. So our answer actually should go to 1 decimal place in this case. We would need to look to the right there at the 1, and because of that, we would just drop it. So our proper answer here would be 7.4. 7.4 has 1 decimal place. How many significant figures does it have? It has 2, and that can be really important. For example, if you take that number and then like use it to multiply afterwards, right? Or divide afterwards. So sometimes, we're looking at significant figures. Sometimes we're looking at decimal places, we're adding and subtracting. And again, if you're doing multiple calculations, sometimes you need to kind of go back and forth, like, okay, that's 1 decimal place, but now we're going to need to look at significant figures. The reason we take the least in each of these cases is your calculation is only as good as your worst measurement, and your worst measurement would have the least number of sig figs or least number of decimal places. So your calculation is only as good as your worst measurement, and that's why we always look at least. Any questions on that there? All right. So let's also talk a little bit about rounding. And we kind of touched upon as we are going through some of these examples, but we do follow normal rounding rules, which means if the number you want to round to, we then look at the number next to it. So if you want to round here, we would then look at the number right next to it. And if that number right next to it is less than 5, typically speaking, we just kind of drop the numbers if necessary. If that number is 5 or more, we round the number up that we want to end at. We again do not want to do any crazy rounding. As I mentioned before, you don't want to ever change the meaning of the number. So, again, if you had something like 13,333 and wanted 2 sig figs, once again, 2 sig figs would take us here. We should look at this number as less than 5. Again, the proper answer here, 13,000, no decimal, our scientific notation, 1.3 times 10 to the 4. Once again, 13 is not an acceptable answer as it is 2 significant figures, but again, a very big difference between the meaning of 13 and the meaning of 13,333. So again, it is sometimes a very common error that people make. As I mentioned earlier, they're just so focused on I need to get the right sig figs that they forget and just kind of go crazy on the rounding. In addition to that, speaking of rounding, if you are doing sort of multiple calculations in a row, so for example, if you did a calculation, you get an answer, and then you're going to take that answer, do another calculation with it, and get an answer, maybe do another calculation with that number. It is really good practice not to round till the very end. And you could keep a couple of extra digits as you're going through, but you do want to kind of not round to the end. If you round really strictly all the way through, every time you get an answer, you're going to be very far away from the true answer. And that's because you're going to create rounding error by doing that. So it's a really good practice not to round to the very end. If you, for example, get an answer and you're like, okay, it should be 2 significant figures, maybe take a few extra digits and continue on with the calculation. Maybe take all the numbers in your calculator and continue on. But you do need to keep track of it all the way through your calculation. So if you're doing multiple steps, the very last step that you do will oftentimes determine where you should end up. But in order to make that decision correctly, you also need to keep track of what you did along the way. So you know really what number of significant figures you have at the end or decimal places you have at the end. So it's important to keep track of it all the way through. Sometimes people will put like a little line above a number to go, okay, that's where this should really be rounded off, and not round off until the very end. But you do gotta kind of keep track of it and round it off at the very end. Any questions on that there? So as I mentioned, 4 or less, we typically drop. 5 or more, we round. Also, again, if we're doing multiple things together, so if I was doing this calculation, for example, the math rules would tell us I probably would start with what is in the parentheses first. So what's in the parentheses is typically where you would start with this calculation. And what we're doing in the parentheses is multiplying, which means we're looking at significant figures. Again, this number here would have 3 significant figures. This number here would have 2 significant figures. That means when we're done with the top part of the calculation only, we technically should have 2 significant figures. And the next thing that we would do is take that number that technically has 2 significant figures and divide it by the number on the bottom, which has how many significant figures? Has 4. Yeah. So basically, we're going to take 2 significant figures divided by 4 significant figures. My answer actually should end up with 2 significant figures, really based on this calculation here. So it may not even be the last one. What really is determinant is that one. So if we did this, for example, and I did, maybe it turns on, 32.1 times 12, that's going to give me on top, if I actually punched it in, 385.2. We're going to then divide it by 4785. Now, personally, I would take that whole number and divide it. But we do know that if I did stop the calculation right at this point, this is technically where we should end up, right? We actually should technically end up for the top number somewhere like 390, right? And again, I would not round at this point to 390. I would probably take the whole number there and then divide it by the bottom number, which would be 4785. And that's going to give me on my calculator here 0.080501567. At this point, because I didn't round, but I did keep track, like, okay, that's 2, and then that is 4. Now I know when I get down here, I'm not going to have really any rounding error because I didn't do any rounding to begin with. And now I could just go to 2, which actually would be this guy. And because that is a 5, we would actually round up in this case. And we would end up at 0.081 would be our proper answer. So again, it's really important not to round too much until the very end, but you do have to kind of keep track of everything that you're doing sort of along the way. Question on that there. Question. Now, this also includes if you're kind of comboing like adding and subtracting, multiplying, dividing. So for example, let's just say I took so let's just say I took this 9655. I'm going to divide it by 36, and then I'm going to add it to 0.156. Okay, so let's take a look. So in this case, we would probably do the division first. So we're going to divide here. So I'm going to take 9655 and divide it by 36. That's going to give me on my calculator, I'm just going to write the whole number here so you can see it's 268.1944444. And that's basically what we get coming out of this part right here. Now, since we're technically dividing, we should be looking at significant figures here, right? And the top number has how many significant figures? 4, and the bottom number has 2. So technically speaking, the number, if we were just to stop the calculation at this point and give an answer, should have 2 significant figures, which technically would be right about there, right? Which means technically this would round to 270, yeah. Now, I personally am not going to round it to 270 at this point. I'm actually going to just continue on with everything in my calculator. If you don't want to continue on with everything in your calculator, take a few digits to the right of that and keep a few digits or so to do that. But I'm going to really take my whole number there, and then I'm going to add now to 0.156. And if I add that to 0.156, I will end up with 268.35044444 on my calculator. Now, technically speaking, the last calculation step I did was what? It was adding, yeah? And when I'm adding, I should be looking at significant figures or decimal places. Decimal places. So technically speaking, my original number I had on the left technically would have how many decimal places? Actually, it would have none, right? Because technically this is what that answer should be, right? It should actually be 270, which would have no decimal places. And I just added it to this number, which technically has 3 decimal places. So really my answer should be now to the whole number, right? And it should be something like 268 in this case, because technically that's what it should be. Now, if I took the whole number, those are all not significant, right? So I do have to keep track of it and then sort of figure out at the end, what it should be. I don't want to round because now if I took 270 plus 0.156, I would end up with 270.156, right, as my answer if I just rounded straight up. And now when I go to my whole number, I'm at 270. So there is a little bit of a difference, right, between those two answers. And that was created because I rounded too early, right? So again, if you even kept a few digits to the right, maybe 3 or 4 digits to the right of what it should have been, and you kept like 268.194 plus 0.156, again, remembering that's technically where it should be. You go 268.194 plus 0.156 gets you 268.35. Once again, this guy should have really no decimal places. Now we're still at 268, which is really what the answer should be. So you don't necessarily have to keep all the digits. You could keep a few, 3 or 4 more than maybe you need. And again, that will help without creating such big rounding errors along the way. Any questions on that? So if you're doing multiple steps, you do have to kind of keep track of what you're doing. And sometimes you do have to kind of go back and forth from like decimal points to sig figs or sig figs back to decimal points. Ultimately, you end up with what you did last. But in order, again, to sort of evaluate that correctly, you have to kind of know what you got going on in terms of the numbers for all the calculations you did before it. So you have to kind of keep track of it. And again, like I said, sometimes people keep track of it like, all right, I'm going to use most of this number, but I know that is where it should technically end. That's where that number should technically end. They'll sometimes put a line over the number where it should technically end and then kind of continue on with a few extra digits so they don't get any rounding errors. Any questions on that there? On what we've been talking about, calculations, sig figs, rounding, any of those things? So, okay. All right. So then again, a reminder that just rounding rules here. We have this number on our calculator, which again, our calculator doesn't always give us the right number of sig figs, usually not. If we need 3 sig figs, that would take us to the 2 here, and we would drop the rest as that's a 3. If we needed to, obviously here, we would go to the 4 and look at the 2, and we would actually just drop them. So again, here on the case of the 2 sig figs, and really the 3 sig figs, we don't want to add zeros. Otherwise, obviously, we're going to have too many sig figs. So in this case, we just want to drop it. It doesn't change the meaning of the number or anything like that. Same thing with the next one there. 3 sig figs would take us to the 7. The next number is an 8. So we would round up. And that would get us 14.8. And then for 2, we would look at the 4 and look at the next number, which is the 7. We would also round up, which would take us to 15. And lastly there, we're going for 3, which would be the 5. Looking at the 6, going to round up. And again, looking for 2, which would take us to 2 sig figs here. And we would look up here, and we would also round up to 3,300. Once again, you could also use scientific notation if you wanted to. All right, so for this one here, if I wanted 3 sig figs, what should it be? 3.15, yeah, grams. Again, we would look here, and that would make us have to round upwards. If I want 2 sig figs, we're now going to kind of come back to here, and we would look at the 4, and in that case, we would just drop it 3.1 grams in this particular case. Any question on those 2 there? Yeah. Yeah. For B or for B, yeah. Yeah, so what you want to do is, if, for example, if you need to go like 2 sig figs, like we needed to in that case, what you first really want to do is figure out where the second significant figure is in their whole answer, and that would be the 1. And then you always, when you're sort of rounding, once you figure out where you need to kind of end your number, you always then want to look to the number to the right of it, and that's what determines whether or not you got kind of either round up or maybe drop it, or in some cases you may even just put some zeros in there and stuff like that. Yeah. Other questions? All right. All right, so take a moment here, adjust each of these to 3 significant figures. You just want to identify where that significant figure is, and 3 in this case. So the first one would be here. We then would look at the number next to it, and that definitely is above 5 there. So we're going to round up, and that looks like it should be an 825. We do need our units as well, centimeters in this case. Question on that one. Next one, once again, we're going to identify our third significant figure. So just like we were counting previously, that 0 is not going to count. That's where we start counting. And that would mean the 2 here would be our third significant figure. Once again, we're going to take a peek at the number next to it, which is a 4. So in this particular case, we are going to just drop the rest of the digits. Once again, we cannot convert those digits into zeros. Otherwise, we would have too many significant figures. Yeah. So we've made all those guys at the end zeros. We would then have 6 significant figures, which is obviously more than 3 that we're looking for. Any questions on that one there? Lastly, here, our third significant figure is not on there. Yeah, so it'd be somewhere right around there. So in this particular case, we actually need to put a 0 in to get us to 3 significant figures. So 5.3, and we're going to add that 0. Now we do have 3 significant figures, as that 0 is going to be significant because of the decimal point that's actually there. Otherwise, we have only obviously 2 significant figures. The other way we could also achieve that, by the way, with any of these, is we could have gone scientific notation, and we could have done a 5.30. Actually, not in this case. I guess you couldn't really do too much because you can't 10 to 0. That wouldn't work. But we could have also done scientific notation actually on these two. Yeah. Yeah. It is. You know, it's like a 1. It's kind of like a 1. So I was just making sure you're paying attention out there, you know. Not that I screwed that up terribly bad. Well, look, hey, chemistry really wasn't my thing. Don't feel bad. That's all right. I know that's reassuring. 112 would be good. Also, writing the right number is probably pretty helpful, I imagine. You know, as they say. Yeah. Yes. Thank you very much. So it should be 0.112 along the way. Thank you. Other questions on that? All right. All right. All right. So as we were talking about, just kind of go through some of these things again. Multiplying and dividing, again, we're looking at significant figures, and it is the least. So as we go through it here, on the top is technically what we would do first, and we're multiplying. So that's 2 significant figures. That's 4 significant figures. That means, technically speaking, the top should have 2 significant figures. We are then going to divide it by the bottom number, which has 3 significant figures. That does mean that we should end up with 2 significant figures. Once again, we can see on the calculator, that's going to take us to the 4. The next number is a 2, so we'll just drop the rest of those numbers, and that is the proper answer. By the way, if you're writing that many digits probably on your test or quiz, that's like way too many. Yes, probably as well. I've had somebody once like wrap the numbers around the back of the page and stuff like that. Too many. All right. Adding significant zeros. So once again here, we got 3 significant figures. We got 3 significant figures. We're dividing, which means, again, our calculator does not always spit out the right number of significant figures. This is only 1 sig fig here. So once again, much like we did on that last one, we would have to add a couple of zeros for the significant figures. We clearly want to make sure that we do not just make it 400 or something like that, right? And change the meaning of it. So we do need to go 4.00 and add those. Now, again, these are going to be significant. And again, that's going to be our decimal point that makes them significant. All right, so why don't you do this one? What should the proper answer? Okay, let's take a look. So again, in this case, we would do technically what's on top first. And again, we're multiplying. So we take 5 times 3.48. Technically speaking, on our calculator, we got 17.04 happening there up on top. Here we are multiplying, so we would be looking at significant figures. This number here has 3. This number here has 4, which means, again, technically speaking, if we were to give an answer for just the top part, we actually should end right about there at the 0, basically, right? Which is technically 3 significant figures. The next thing we're going to do is divide it by 2. Once again, here, I'm not going to round at this point. I am just going to divide it by 2 with the whole number there, the 1704. And if I divide it by 2 on my calculator, I get spit out to me 8.52 in this case. By the way, the centimeters on top and bottom would cancel, and that would leave you still centimeters as the units that are there. Here, the bottom number has 2 significant figures. So really what we're doing at the very end here is taking a number with 3 significant figures, dividing it by a number with 2 significant figures. And that means that we actually should end over here with 2 significant figures, which would be the 5. And this should be 8.5 centimeters in this case. Yeah. Any questions on that there? So again, you do have to kind of keep track of it as you're doing calculations. Once again, I would not round to the end and kind of clean it up there once you get to the end. Any questions on that there? Go. That is definitely not the right units they have on that. So adding and subtracting, as we talked about, once again, we are looking at decimal places. And also, as we saw in sort of that made up example I did the other a little bit earlier, again, if you have a whole number, the smallest number of decimal places, it's whole number. So if you do have a whole number and an addition or subtraction, you then should take everybody, kind of the whole number as the answer. Once again, we're looking at decimal places here. So 3 decimal places, 2 and 1. This is what we got on the calculator. We would go to 1 decimal place, and that technically would be our answer. It has, once again, if we were going to use it in another calculation, it has 3 significant figures. So again, as we talked about, you might have to transition from like significant figures to decimal or decimal to significant figures. Same thing for subtracting. 2 decimal places, 1, we should end up at 1. Here we're going to round up because that's a 9. And that would again give us 62.1, which is 1 decimal place. Okay, if we punch this into our calculator up on the display, a 104.409 in this case, milligrams. Once again, we're adding, so decimal places, 3 decimal places, 1 decimal place, so we would go to 1 decimal place. So a 104.4 milligrams would be our proper answer in this case. Again, has 1 decimal place, but does have 4 significant figures if you were going to go on and use it with its significant figures. Question on that one there. All right. All right, question on calculations, significant figures, how to do all that there. Oh. Okay, we're then going to get into kind of conversions, equalities, and doing dimensional analysis, which is an important calculation in chemistry. So let's start with prefixes. There are a lot of prefixes that are sometimes used to sort of change the meaning of a number, especially in the metric system and also the SI system. For example, 1 kilometer is 1,000 meters. 1 millimeter is 0.01 meters. And again, the prefix itself doesn't really change regardless of what sort of unit you're dealing with. So, for example, if you have 1 kilometer is 1,000 meters, you would have 1 kiloliter is 1,000 liters, 1 kilogram is 1,000 grams. So they're all the same sort of conversion, if you will. It doesn't really matter what the base unit is. So sometimes we refer to these as, on this side, the prefix unit. And this is the base unit. So in the case of the first one, meters in both of them. So that's sort of the unit we're dealing with. Liters is in both of them. That's the unit on that one. Grams is the base unit on each of those. So we do use prefixes, and there's kind of two ways that we sometimes use these prefixes, and sometimes people do use them sort of incorrectly. So let's talk a little about a table like this, which you have in your book. And a lot of times people will look at the scientific notation part of it, and they will use it as the conversion. And you can, but sometimes people will do it incorrectly. So for example, if you see kilo, which is a common one like we just saw there, kilo basically means 10 to the 3. And what does 10 to the 3 really mean? It's in scientific notation. It really is 1 times 10 to the 3 is basically what that means. So any of these here, these are all 1 times 10 to the whatever it may be. Mega 1 times 10 to the 6, giga 1 times 10 to the 9, and so forth. So when we use this as sort of a conversion factor, it is really, really common. People will always do it backwards. So when you see this number like 10 to the 12, 9, 6, 3, that is how much there is in the base unit to one of the prefix units. So when we talk about a kilogram, that is the prefix unit. And that would equal 10 to the 3 grams. Grams is the base unit. It is very common. People will always do this one backwards, not just this particular one, but all these backwards. They'll sometimes look at a table like this and go, there's 10 to the 3 kilograms in 1 gram, and kind of do it backwards. So that is always how you do it. Once again, as we saw on the previous slide, it doesn't matter if you're dealing with grams. It doesn't matter if you're dealing with meters. So 1 kilometer would be 10 to the 3 meters. So again, it could be anything just like we saw in that one. 1 kiloliter is 10 to the 3 liters. So that is the proper way to use that. Now, you might be saying it wasn't on the last one, 1 kilogram is 1,000 grams, and it was. And that's because 1 times 10 to the 3, if you turn it into a number, means you go 1, 2, 3 places to the right, put in some zeros, and now you have your 1,000. So that is, where we get that sort of number from. So you can use, it like this. You could use it like this, but you do want to make sure that you do it correctly if you kind of use that 10 to the whatever. By the way, if you're going to put that into your calculator, you would put it in, you do in scientific notation like we talked about in chapter 1, 1 exponent button 3, right? So again, you want to make sure you use your exponent button if you're going to put that into your calculator, just like you were doing scientific notation. Here's some others, for example, centi, milli, micro, nano. So for example, centi, when you look on that, is 10 to the minus 2. What right there. And again, that basically is 1 times 10 to the minus 2. And the way that we use this correctly is, again, in one of the prefix. So let's say we were doing centimeters. There would be 10 to the minus 2 meters. And again, that is the proper way to set that up. If I had 1 centigram, that would be 10 to the minus 2 grams. So again, the 10 to the minus 2, the 10 to the whatever, always goes with the base unit, and it's always 1 for the prefix unit. Now, again, you may also know that there are 100 centimeters in 1 meter. And the way we get that is by taking this. If you take 1 centimeter equals 10 to the minus 2 meters, and you divide both sides by 1 times 10 to the minus 2, those guys cancel, and you get 1 meter is 100 centimeters. So that is where that comes from. So this is a legitimate conversion. So is this. But again, it's very common that sometimes people will do it backwards, and again, do something like 10 to the minus 2 centimeters is 1 meter. So you don't want to do that. You want to make sure that you use it correctly. So for example, if I had nano, which is on that list, and nano is 10 to the minus 9, and let's just say that we wanted to take 455 nanometers and we want to know how many meters that was, for example. So what we could do is, again, go to this table, look up nano, which will give us that conversion there. Again, we want to use it correctly, which is, in this case, one of the prefix, which would be nanometers, equals 10 to the minus 9 meters. This is what is referred to as an equality. An equality, again, is basically two values that are on different unit scales, but represent the same amount. So for example, both of those things, you say you have 1 nanometer or 1 times 10 to the minus 9 meters, that represents the same sort of distance or length. It's the same idea if you said I had 100 pennies, that represents $1, right? It represents the same amount of money. They're just on different sort of scales. And that's what an equality is. And why equalities are important is we could actually write conversion factors for equalities. And the way we write conversion factors is they are basically fractions. And we could have 1 nanometer up on top divided by 10 to the minus 9 meters on the bottom, or 10 to the minus 9 meters up on top, 1 nanometer on the bottom. And these are what are referred to as conversion factors. And from any equality that you have, you essentially can write two conversion factors. Again, they're just fractions. One goes on top, the other goes on the bottom, and flip it. The other guy goes on top, the other guy goes on the bottom. And the reason we use conversion factors is when we set up problems, we do it what is known as dimensional analysis. And the idea of dimensional analysis, as we'll talk more about probably next time, is we set it up using conversion factors so that we could kind of see units canceling. And this is the way you kind of show your work in chemistry, is through dimensional analysis. And it's a very sort of straightforward idea of, if I have this unit here up on top, for example, and I want to get rid of it, in dimensional analysis, you put the same unit in the opposite location. So if I have unit A up on top and I don't really want unit A, but I want unit B, I could put unit A on the bottom, unit B up on top. And what that's going to do is cancel out unit A, because when you do dimensional analysis, it is always this math, which also makes it pretty easy for people, because all you have to remember is anything that's up on top gets multiplied. So anything up on top gets multiplied. Anything on the bottom gets divided. So basically, if you set it up this way and do the calculation this way, all you have to remember, multiply on top, divide on the bottom. It's also very, very convenient, as we'll talk about, that in a lot of cases, you may not even have to use an actual formula and rearrange the formula. You could just set it up like this to get rid of the units you don't want, keep the units you do want. And all you have to remember is, okay, cool, up on top, multiply, on the bottom, divide. And opposites always cancel. So if the unit's on top, you need to put the same unit on the bottom. But if the unit you want to get rid of is on the bottom, you need to put the same unit on top. So always opposites to cancel, multiply the top. So the reason this works is, in this case, unit A will basically cancel out unit A on the bottom. And that's because ultimately what we're doing math is we're taking unit A divided by unit A, which basically equals 1. It's the same idea in math. If you took 2 divided by 2, it equals 1. They basically cancel each other out. 4 divided by 4 equals 1. If you have the same unit up on top and bottom, you're dividing, basically equals 1, and essentially cancels each other out in a sense. So we could take the approach of dimensional analysis with this problem, and we are going to start with the number that we were given, which is 455 nanometers. Now, if it helps you, it is not really written as a fraction like this. You can write it as a fraction. All you have to simply do is just put it over 1. And now what that allows you to see is, hopefully, my nanometers are on top or bottom? Top. Which means if I want to get rid of nanometers, I need to put it top or bottom? Bottom, opposite, right? And that makes the decision of what conversion factor I should use pretty simple, because which conversion factor here has nanometers on the bottom? The one on the left or the one on the right? It is this one, right? This is the one that has the nanometers on the bottom. So that is all I need to do is this move right here. And again, we're going to multiply what's on top. We're going to divide by what's on the bottom. And once again, essentially what we're doing is dividing nanometers on top by nanometers on the bottom. They are going to go away. By the way, the unit I'm left with now is meters, and it's on top, and that is the unit I'm looking for. So now that I know, okay, opposites cancel, up on top is what I need to punch in. I'm going to multiply. I don't even have to really think about math-wise rearranging anything. I'm just going to grab my calculator, take 455. I'm going to times it. Again, the 10 to the minus 9 is 1 times 10 to the minus 9. So on your calculator, you might need to punch it in that way, just like scientific notation, 1 exponent negative button 9. And punch that in and hit equals. And you will get on your calculator something with a lot of zeros. Should have went the other way. Hope I didn't lose any along the way there, I hope. So you end up with 0.000000455 or 4.55 times 10 to the minus 7. The units here are meters in each of these cases. And that would be the answer there. And that would be the conversion and the way you could show your work through dimensional analysis. And again, it really is, as we'll talk about a little bit more next time, it really is a really good way to do your work. Because like I said before, you sometimes don't even have to remember formulas or have to arrange formulas. You might not even know the formula, but what you do know is like, I know I don't need those units, but I need to end up with these units. And you could kind of set it up that way. And again, you pretty much are always going to be doing multiplying and dividing, which also helps you with your answer. Because if the only thing I'm doing is multiplying and dividing, when I do my answer, I should look at sig figs or decimal places. If I'm multiplying and dividing sig figs. So I know at the end, my answer should be based on sig figs. And since we talked about this, that is a metric to metric conversion, which is an exact number, which means I don't even have to think about that one. That means the only real number I have in this problem is this one, which has how many significant figures? And my answer has how many? Which is good as well, right? So I'm good to go in terms of my answers and significant figures as well. Any questions on that there? All right, we're laid up. We'll